Hello, everyone. I hope you can hear me well. This is Marina Manganaro from the University of Riega, and I'm here today with you for a new live event of Meet the Magicians. So today we are going to show you very interesting results, but first let me remind you a bit what is magic exactly. So this fantastic name indicates a collaboration of many scientists which are working in very high energy gamma rays. So our telescopes are able to work with photons which are very, very energetic. But now, why we have this fantastic name? Of course, it is an acronym, and I want to remind to you what that means. So MAGIC stands for Major Atmospheric Gamma Ray Imaging Cherenkov Telescopes. So as you can see from this image of our telescopes, we have very, very special telescopes. Probably you have never seen something like that. Our telescopes are two. They are named Magic 1 and Magic 2. And for detecting photons which have such a high energy, we need a very special experiment. So you see, it's impossible for us to see directly these photons when they are so energetic and they have such a high frequency. What we can do is to study the Cherenkov light, which is produced when these photons enter the atmosphere and interact with the atoms of the atmosphere. Then you have fantastic showers of particles which are produced, and the Cherenkov light is reflected on our mirrors, and then it goes straight reflected into this camera, which is this big cube on top of the mirror dishes. So this very interesting method to detect very high energy gamma rays, it's now used by different arrays of telescopes around the world. But today we focus, of course, on our beloved telescopes. Here in this other scheme, you can see how the photons, they enter the atmosphere and they are so energetic that they produce a shower of charged particles, and these charged particles are producing the Cherenkov light, which is blue. So it is in the visible range. So at the end of the day, we are kind of optical telescopes, even if we study very high energy gamma rays. Okay, here on the left bottom part of this scheme, you can see a little image of showers of particles and this characteristic shape, which is a bit elongated. And we detect all these images, and we study the data, and we can reconstruct the position of the source and the energy of these gamma rays and everything. And so we can produce fantastic results. But now let's go back to what we want to do today. I just wanted to remind very shortly that our collaboration counts a lot of members. Actually, today we are almost 300. And then we have people from 12 countries. Actually, Norway just joined. So now we are 13. But okay, our members study very high energy gamma rays and then produce many papers for our collaboration. And today we are going to talk about a very new result about dark matter. And this is why we decided to do this masterclass on dark matter, in which our teacher of defense from the dark matter, Tomohiro Inada, will tell us everything about this fantastic result. So now let me bring to you and introduce you Tomohiro. Tomohiro. Hello, Tomohiro.
Hi. Hello.
Tomohiro
Nice to see
is
you. Yeah.
Tomohiro is one of our magicians, and he works in Japan. So Tomohiro, welcome here, and please can you tell us something about you?
Yeah, thanks a lot. So I'm pleasure to be here. So I'm Tomohiro Inada, working in Institute for Cosmic Ray Research in Japan, University of Tokyo, and I'm a researcher there. And I have working for the with magic in the magic collaboration for a long time. And this time we publish a new paper about the dark matter search around the galactic center. And with our colleagues, unfortunately, our colleagues cannot make attendance today. So, but yes, so Daniel Kashbeck from IFAIE in Spain, and also Moritz Hutten from ICRR, previous in Max Planck Institute in Germany. So we are making an international collaboration to make this new result in this time. Yeah. So
here, Tomohiro, we see an
and
image.
right, yeah. So this is kind of this is a building of our institute in Japan. So so this institute hosts a magic institute, also a joint magic institute, a magic collaboration, and also the Chenkov telescope array in the next generation of the magic. It's kind of the newborn telescope. Yeah, so it's joined many projects in the astroparticle physics field.
Yes, we have many magicians from your institute in Tokyo. And as you rightly said, this new result that we are going to show was led by you together with other magicians, in particular Daniel Kersberg and Moritz Wetten. They can be here with us today because astrophysicists are super busy, and so. But we have met them before on Meet the Magicians, and probably we will meet them again. So we say a big hello to them. I hope they can follow us, but they are super busy, so I'm not sure. Anyway, it was a team work of you, Daniel, and Moritz, using magic data. Okay, Domohiro. So this article about dark matter lines in the galactic center was just published a few days ago in a very important journal. So we scientists are obliged, but are also happy to show our result in important scientific journals. This is very important to us, and so we are very proud that this work is published in Physical Review Letters. Now, Tomohiro, our followers, they are not all of them super expert, but they are very curious. So I wanted to ask you if you can very quickly, simply show us this beautiful paper and tell us something about this work. Okay?
Okay, yeah, thanks a lot for the introduction. So yeah, this is the paper we published last 2 weeks ago, a few weeks ago, and it's called Search for Gamma Ray Spectral Lines from Dark Matter Annihilation up to 100 TeV throughout the galactic center with magic. Maybe there are many confusing words, so yeah, don't worry, we explain it later briefly. So but before we go to detail, we can quickly go through the paper. So we have many collaborators from the many countries and institute, as Marina said. And yes, all magicians are very important to make this result. So yeah, thanks again to all collaborators. So let me appreciate here again. And so then we go like this, and so physical review letters accept only a few several pages. They're not like long papers. So this is 1, 2, 3, 4, 5, 6, 7 pages. So only 7 pages here. But this only 7 pages includes our 7 years of our studies, 7 years of our observation time. So 1 page is corresponding to 1 year observation. Yeah, something like this. And here the important results are here. Oops. And so this is kind of the important plot from our papers, and it means it's a bit detailed. So this means unfortunately we cannot find the dark matter, but we set kind of our knowledge to how to say, in spite of undefined. So in spite, despite we don't find dark matter signal, but we got some hints to put some to say something about the dark matter model or particle. So this plot means like this, and yes, yellow band and green band says like the possibility to be possibility to exclude dark matter border with this region, something like this. So yeah, this is kind of the important plot, one of the most important plots in our paper. Yep. And yeah, so yeah, so I don't go that's here now, but yeah, we try
Yes,
to
yes.
explain in detail, yeah, one by one. Yeah.
Yes, thank you for showing us the paper. It's exciting to see. Of course, it's not many pages because Physical Review Letters is a journal that presents very shortly important results. So it is a high impact journal that condensates all the results in a short number of pages. In other scientific papers, we can have more pages, but Physical Review Letters is very condensed. Okay, so you showed a very interesting plot, which is also very difficult to understand.
Right. Yeah.
But this is a kind of, we call it Brazilian plot, I guess, for the colors. And yeah, as you said, you didn't find the dark matter, but this is not that we can, okay, I think everybody knows that it's not easy to detect dark matter, but it's anyway a very important result because you can exclude some models and you can set upper limits, which means, okay, I don't see it yet, but my experiment is gone up to this level. So if we increase the sensibility of the instruments, we can have better results. So this for astrophysicists is very important, even
Right.
if normally people want to know, but do we have aliens? Where is dark matter?
Right.
But for us, this is a super important result. So science goes slowly, learning little things time by time. Okay, so well, fantastic. And now that we have seen your beautiful baby, this fantastic paper, maybe we can go a bit, a bit. A bit. I forgot the word.
A bit of like not contents, but kind of like how to say, like nice pictures of.
No, I wanted to say we showed the wide picture, the paper, and now we can go a bit
deeper inside, or
thank you, Tovira. I know you are trying to help me, but I lost the
no.
word completely. Well, okay, let's say just what I want to do. Let's talk a bit about dark matter in general. Okay, so
Right, yeah,
you are our
of course.
teacher of defense against the dark matter. So tell to our followers something about what dark matter is. Okay.
Right.
Thank
So
you.
yeah, welcome. Yeah. So now I would like to explain so what could be dark matter. So it's shortly saying no one knows what it is, but we are trying to explain what with what we knew already. And this I share one picture, nice pictures, showing the galactic center and the velocity. And you see the nice picture of galactic center. And yeah, so we in the past, like 100 years ago, so one scientist who is a Belarusian tried to measure the rotational velocity of the galactic galaxy. And yeah, and usually if something is rotating, then it's if you measure the outer layer of the velocity, then you show this kind of this kind of distribution, but she found something different from we expected. So then she solves something like this. And from this results, this is now kind of the first evidence of the dark matter. So and so like in that time, like she found like something like with masses, like some weight masses are located in the center of galaxy, our galaxy, but we don't know what it is. And she tried to observe it with the telescope, but we didn't see anything. So that's why we call it dark matter. So like we don't know what it is. And after time passes, we try to catch it with another way. And I want to share something. So it's another way to explain catch the dark matter. So this is called gravitational lensing. So yeah, so you see the many nice bright galaxies, and some astronomer found like the strange shape of the galaxy. And you see that some galaxies are usually galaxies are kind of uh, it's kind of circle or just a bit elongated, but yeah, one finds the galaxy is kind of the shape of galaxy is kind of becomes like banana shape or some elongated shape. So astronomer found such features in the data of the telescope, and they try to find what it is, but they in the end they reach this is due to the elongated image of the galaxies. As you see, like for instance, you can imagine like you have a kind of a glass, and then from glass or like some pool or like water whatever, like if you see something in the water, then it shows that light. You see you see the object with different position with because light has shows some curves. But same things, similar things happens in the universe. We don't see anything, but something is filled in our universe. And if light goes inside something, then it doesn't go inside, but it goes like it shows curve like this. And it tries to avoid the object, and then it shows like some curves. And that's why some images are split. Then we saw that many galaxies like this, and it shows like it's kind of lens. So that's why we said it's a gravitational lensing. And it's kind of this is also indirect evidence of dark matter existence. And yeah, so this is kind of astronomical, astronomical evidence of dark matter existence. But then what we know about dark matter? So we know that something exists in our universe, but we didn't get, we have not get in our hand. So that's why so many experiment physicists are trying to get in our hand, and our new results are one of them. So we try to catch it in our hand and try to explore, try to discover what is exactly dark matter made of, something like this. So
Yes, so
yeah,
we don't see it directly, but we see experimentally many effects which are produced by the existence of dark matter. So we hope to finally, at some point, understand exactly how dark matter is made of. But for now, we are sure that it's there because we can see, as you showed already, the effects of its presence. So gravitational lensing that you are showing here is one of these wonderful effects. But now I am wondering now how we think that dark matter is composed. What can it be made of?
So, so this is, sorry, so this is question, right? So this is what
Yes,
we made.
yes, yes. I'm
Yeah, so
asking you.
actually, this is also a question to this, my question. So what dark matter is made of? So we are trying. We actually, we honestly, we don't know what it is, but we are trying to explain with our knowledge. And in the like the possibly we are thinking it to be a new particle we beyond our knowledge. It's called a like particle beyond the standard model. So we know where. So the with as you might know, like many particles were discovered in the past, and well, and yeah, and but still we don't know. We might have something, some particles we don't know. So if dark, so we are thinking, physicists are crazy. So we are thinking dark matter would be like new particle like this. And it's called like supersymmetric particle would be the one of the good candidate. And yeah, so I'm showing like new. So and yeah, so like many particle models are like expected, and one of them called like a supersymmetric particle, and it's called a SUSY, and it's already it's many experimentalists or physicists are trying to catch it, but no one detected. And yeah, and so for our research, we're trying to get very closer. And now I want to share some crazy diagram. So yeah, something like this. Yeah, thank you. So yeah, so our way to search new particles are like this. So like we are trying to catch the product of dark matter annihilation. So that's why our paper has like the title of our paper is dark matter annihilation. So yeah, we think dark matter dark matter is a kind of new particle, and we don't know. And there are many particle model, but anyway, any new particle model. And if dark matter particle meet each other, then they can, according to the model, then they can annihilate each other and make new particle, make a particle we know. And it's kind of it's called a Feynman diagram. It's kind of like many crazy particle physics like this kind of drawing. And for instance, like left upper diagram and left middle upper diagram shows like how dark matter was produced. So dark matter annihilates into the particle we know. Like for instance, left upper case, it says like dark matter particle, dark matter particle annihilates into the two photons. And in the middle of part, like we don't know what happened inside, what happened in the middle, but in the end, in the final state will be photon. So we try to catch this photon with a magic telescope, because magic telescope is very sensitive to like high energy photons. So we try to catch these photons, and also we try to catch another case, like this is called like Z boson, so which is like weak interaction. It's another interaction, particle interaction, yeah, it's called a weak interaction. And yeah, we try to catch this. So we don't. So magic telescope can try to can be sensitive to catch this this one photon. So we try to catch this kind of feature in the final state from dark matter annihilation. And we are thinking like so this is like kind of also diagram, upper right shows a diagram. So we are thinking like this is also crazy things, like if dark matter annihilates each other, then it makes interfere each other, then in the end it shows like two photons. So also we are thinking this kind of diagram. And in the end, so what we saw is kind of like it's called a line emission. And we try to, it's really clear signal. So like you see the bottom plot, and this is kind of the like feature from dark matter annihilation. And the magic telescope is trying to catch this kind of shape. Which is called the energy spectrum. And we try to catch this kind of specific energy spectra from dark matter annihilation. And among of that, we focus on the like line-like emission, so-called. So you see the some peaks in the mass, in the dark matter masses, and this is very clear signal compared to other spectra. Like you see the clear peak at the dark matter masses. Then, if we see something like this, then we can get Nobel Prize for sure. But yeah, so this is kind of our strategy to search for dark matter. And yeah, so and also we are thinking dark matter is made of like new particle we don't know, and it makes a new and the new particle. Dark matter is new particle, but dark matter can produce the particle we know, and we try to catch the such particles in the end.
Yes, this is very interesting. So we can find try to find the search for dark matter from a different possible process that can be studied, like annihilation or decay, as you said. Fantastic. But where these processes are most likely to be studied, which are the places in the universe in which we presume, we think we have more evidence that we could find the dark matter, which are the targets, let's say.
Right. Yeah. So yeah, that's good target. So yeah, good point. So we are particle physicists, but also we are astronomers. So we try to observe astronomical objects in the universe. So we need to think about what is the best target to discover dark matter. So I want to share my one plot. So this is kind of like how to say, the target astronomical sources which could be dark matter sources. Like this is kind of dark matter galactic plane, and there are many targets. Like for instance, galactic halo, and also galactic center, and also galactic diffuse, extragalactic diffuse, a dwarf field of galaxy. So there are plenty of ways we can try to search dark matter. But yeah, and so this is kind of the view from the gamma rays, and I want to share another things. So maybe I should have shared before, actually. So yeah, I want to share another pictures. So
How
this
beautiful.
is right. This is like beautiful. Yeah, this is beautiful like galactic plane and the center, and you see some in the brightness in the galactic center. So you see the many sources, astronomical sources in the galactic center, but this is kind of the view with optical light. So optical light means we can see, right? We can see our eyes. But so if we want to search, if we only think about the dark matter content, then what kind of view we see? So I want to share. So for instance, so this is, you can remember the previous picture, and this is, yeah, so I want to share the view with only dark matter. So you see there are no stars in the galactic plane. You saw with optical light, you saw many stars and many beautiful stars, galaxy, whatever. But if you consider only dark matter, then you see nothing almost. But you see the big cluster in the galaxy center of galaxy here. Then, yeah, you see some hotspot, and also, so these hotspot could be a good target to dark matter search. But apparently, as look at these pictures, then maybe you want to search the center of galaxy, So because it shows the highest expected signal and the content of dark matter. So that's why, like, we try to in the end we decided to observe a galactic center because the largest dark matter content is expected, and then likely to get signal from there, and then for sure dark matter is there. We believe it. Yeah.
I see. So we search in the galactic center, and this is a very important target. But studying the galactic center for magic telescopes is not that easy because, of course, the galactic center is a lot bright. There are many sources of very high energy gamma rays in the galactic center. And so the analysis of this kind of target is very complicated, right? Can you tell
Right.
us
Yeah.
something about it?
Yeah, it's very difficult. Like, for instance, there are many sources as you can like this. You can see like this. So it's super bright. So like previous picture only includes a dark matter content, but it's from it's estimated with simulation. So it's kind of not the real world. But it's real world. So we see something like this. So it's very bright. So yeah, there are many sources. So, but it's very difficult to find that it's kind of tiny signal from dark matter. But so yeah, but to try to catch the signal from dark matter, we so focus on the signal. Like as I said, let me say again. So the try to search like such signal. So for instance, so like like this. So the energy spectrum from the astronomical sources shows like this kind of broader shape. But on the other hand, so the dark matter, the signal from dark matter would have the shape like this kind of peak. It's called line emission. So that's why the title of our paper said like we search for line-like emission. So it's super clear, and no other emission from astrophysical sources. So for sure, if we find this kind of signal, then we can immediately claim we discovered dark matter. So yeah, this is kind of like new technique to search for dark matter signal from many bright, beautiful sources.
So this would be a perfect way to identify dark matter. But what we found in this work, which had so much potentiality mm, to identify dark matter, is, as we said, we didn't find any signal. But can you again explain, because I think this is very important, that for us, this is for us, but in general for the astrophysics community, this makes sense. This is still an important result.
Right. So yeah, this is kind of one plot. So yeah, to explain. So yeah, so I think that this is a bit confusing, but let me try to my best. So yeah, so this plot means like how to constrain our how to say how to constrain our new particle model. So this like gray curve sets like this gray curve sets the theoretical expectation from a new particle, which is called a supersymmetric. And so this colored line, this is kind of our sensitivity. So there are many lines. We assume the many, we assume the different types of the galaxy dark matter profile, but whatever. So then this is kind of anyway. These lines, these colored line set our best performance with our telescope, with magic telescope, and then we try to we got such sensitivity, and with such sensitivity we try to constrain on the new particle model, which is shown as gray curve. And as you see, so if so, delay curve means if a new particle exists, then it shows this kind of feature in the energy spectrum. So then with obtained our performance, we try to be succeed in constraining such models with many masses, and also this you can focus on this blue band. So this blue band is kind of a sweet spot, like how to say. So new particle does not have to be like dark matter, but if new particle exists in this region, this department region, then it could be dark matter. So then how to say, this is kind of very important regions, and so this in our paper we for the first time we constrained this parameter region with the galactic center of the patient. So this is kind of like how to say, the best knowledge we obtained with our studies.
Very good, Tomohiro. So you say that this is the best that we can do right now with magic telescopes and these and other arrays which work in the same in the same energy range, because
Right.
there are other experiments similar to magic in the similar energy range. But you also said that maybe with the better sensitivity we could explore better this region. What does it mean? How can we get a higher sensitivity?
Right. So yeah. So to get the higher sensitivity, we try to to think about it very carefully. And for instance, we try to improve our analysis method, and we specialize to such lines like emission, and also so something like this. Maybe this is a good picture. And so yeah, and this is kind of nice picture with galactic frame, and it's called this is kind of a unique thing in our telescope because our telescope is located in La Palma, which is in northern hemisphere. And as you can see, so like you see the beautiful galactic frame on the sky, but yeah, usually it cannot go so from northern hemisphere you cannot just observe galactic center on exactly on your head. Like always galactic frame or galactic center is kind of like located in the lower region on the sky. And this is kind of a unique thing with our telescope, and making use of this feature, we try to improve. We try to improve our try to improve the sensitivity of our telescope. So this is it's called like large sense angle observation. So yeah, so this is kind of also the how to say, the important ingredient to improve the sensitivity of our telescope.
Yes, on this regard, we can maybe go back a little bit to this image. Okay, maybe this is not the best image to show, but what I wanted to say is that when we change the zenith angle, of course we see the showers not clearly like they come from the top of the telescopes, but they are kind of tilted. So of course you need a special analysis to study the to study our data when the zenith is very high. And in magic we have now uh, we have developed this analysis with a very large zenith angle, and so you say this can help to increase the sensitivity.
Yeah, exactly. Yeah.
Yeah, this is something that also help us to collect more data, because some years ago we had the problem to study these high zenith angles, but now we have all the software that we need. We did our own Monte Carlo simulation in order to cover also the high zenith, and this can give us a lot more data to use also for this and other studies. So another thing I wanted to remind to our followers is that the sky of La Palma is fantastic and super perfect for having telescopes observing, and this is because there is a long story of efforts to keep the sky of La Palma very clean. This happens also in another Canary Island, Tenerife, where there are a lot of telescopes. And to keep the light pollution low, a lot of efforts has to be done, because you need to protect this area from light which is coming from human settlements or from other kind of interference. For instance, on the Roque, you cannot just go with the car and your lights on. There is a strict surveillance to avoid that any light can interfere with the telescopes and with this super perfect quality of the night sky. And also this picture that was taken by astrophotographer Daniel Lopez can show very clearly how the sky on top of Magic is really doesn't have any kind of pollution. It's super clear. Okay, this was just a comment. But of course, I thank you a lot, Tomohiro, for all your explanations. But you are a teacher of defense against dark matter, so you know a lot of things, of course. So we are very happy to have heard about this result from you. And now I have thought to move to questions, because we have questions from the public, yes, and we kindly ask you to answer to those questions, so we can interact with our followers. So we have first question from our friend David. David is one of our best friends in our live events, and David also came to visit us on the Roque. So David asks, what is your best guess as to when we might discover dark matter? When? What do you think, Tomohiro?
Well, so it's really hard to say, but yeah, let's say it might be tomorrow, or let's say very late, like 10 years later or something. But for sure, I think next 10 years, it's really hot time. Like in next 10 years, let's say. So so dark matter will be the very hot topic. Like many experiments, including a magic telescope, and we try to get a new facility. To search for dark matter, and we improved the detectors significantly. Then we try to find we will be able to search like a tiny signal from dark matter, more tiny, even tiny signal now, but we can try to search more tiny signal. Then we may see something interesting. And this is I really expect. I believe it will happen. It will happen in next 10 years. I think. Yeah, I have to say I cannot say for sure, but most likely something happens in next 10 years. I think. This is kind of my my personal opinion and also my hope. Does it make sense, like to the questions? I hope so. Yeah, thanks a lot, David. So, any other questions? Hello, Angela. So how can you know that the gamma rays observed come from dark matter particle annihilation and not from another astrophysical process? Right. So this is very how to say, like good questions. So we have two. With gamma rays, like we have two good points to observe in terms of dark matter search. So like the telescope is observing and seeing the photons. Photon is kind of just it's photon, so it doesn't affect it by anything. Like it can go straight, like without affected by any, how to say, magnetic field in the interstellar medium or of the universe or any other thing. It can go through. So if we see photons from astronomical sources, then the photon comes from the sources for sure. So then we can identify which sources emit this photon. Then if sources is how to say, if those sources have much content of dark matter, then we can say this photon could be from dark matter annihilation. And the second answer is like we see some the specific shape of the energy spectra in case of dark matter annihilation. So if it's from astrophysical, if emission is astrophysical sources, then it should be electromagnetic process. So which we know already. So like we can calculate energy spectra very precisely. Then we can compare we can compare the spectrum, obtained spectrum with the calculated spectra with obtained real data. Then we can see some deviation from our knowledge. Then, of course, we have some expectation for the dark matter annihilation. So like line like peak emission or something like some other things. So then we compare real data with our calculation of electromagnetic emission. Then we can derive the signal, dark matter signal. So yeah, so this is kind of a way to search for gamma rays from dark matter annihilation. I hope it makes sense for you.
Well, yes, I think it was a very comprehensive answer. I hope that Angela is okay with that. Regarding the first question, David is happy.
Yeah, thank you. Thank you too. Yeah, thank you so much.
And so I think we are going towards the end of this event, and it was a very interesting event. I think I hope we can have another one soon. And I wanted at this point, Angela is replying that she
thank you.
liked
Thank you
your
too. I
answer.
appreciate that. I appreciate your question and attendance.
I just wanted to close this event introducing to you our Serena, who is in the backstage. So now I add Serena here.
Hi, everyone.
Hi, Serena.
Hello,
Hi.
Serena. Thank you for working in the
Yeah, I
backstage
appreciate your
today.
working.
It was my
As
pleasure.
you know, Serena is also a magician working in the magic collaboration, and she is also, together with me, coordinator of the outreach and DEI working group. So we thank you so much to join us today, and thank you a lot to Tomohiro, but also to Daniel, Kay, and Moritz that couldn't be here today, but they worked a lot for this project. And see you soon to the next live of Meet Magicians. Thank you.
Yeah,
Bye.
thank you
Bye,
very much,
everyone.
Serena. Bye,
Bye.
Bye
everyone.
bye.
Thank
Bye.
you. Thank you for everyone. Thank you so much.